I'm going to talk mainly about 10.2 today, but as usual I'll go quickly through the material of my pre-recorded lecture, which is on Keats. Just to remind you, this is all about group theory. And let me just remind you, if, as is possible you haven't seen it, this is just to remind you what I am talking about in that lecture. So the idea was to talk about free groups, which is a topic which is not normally introduced in a first course on groups. It's quite a deep topic, and it really comes from geometry and topology more than just algebra. So fortunately we can all make a start on this, because we all know one free group, namely the group of integers. I mean, what is, of course, the integers is a group under addition, so normally here we're working with multiplicative groups. But as a group, the key feature of the integers is it's an infinite cyclic group under addition, but I prefer to think of it as a cyclic group under multiplication. So you have a single generator A, which corresponds to 1 or minus 1, then you have all the powers of A. Of course, A minus 1 means the inverse and so on. So that is a free group in the sense there are no generators, there's no extra relation, apart from you have the obvious relations like A inverse times A is the identity, but that's part of group theory, and that's accepted. But there are no other relations. Okay, but when you want to start talking about free groups on more than one letter, or more than one generator, then you do get something new, in the sense that if you want to define what's called the free product of two groups, there's no relation between, these groups could be the same group, but you've got to use different symbols for them, and there's no relation between one group and the other. So if I want to write out an element of this group, there's no commutativity. So a typical element of this group would just be a word consisting of a string of letters. Now, if two letters belong to the same group, you can obviously, if two letters belong to G, you can combine them and think of that's a single element of G. But you can't mix G and H. So you'll have words with typically you can have sort of G1, H1, G2, H2. But one of these could be the identity, in which case you just rub it out. So if G1 is the identity, you can start with an element of H. But all the other identities are removed. Any identity in either group is removed, except that obviously there's got to be a single identity in the group. So there is a special element in the group which you can write E or 1, which corresponds to the overall identity. So if if there are no elements from G, you could have just H and H inverse. That would give you just your unique identity. And then obviously you can multiply two elements in this setup, because you just have two words, you put them next to each other. That's going to be an associative operation. You can define inverses. For example, the inverse of this four-letter word would be H2 inverse, G2 inverse, H1 inverse, G1 inverse, because when I put that in front of the word, I get the identity and so on. So that in that way you can take what's called the free product of two groups. And the groups could be any groups. There could be finite groups, cyclic groups in particular, or there could be infinite groups. So if you take the free product of two copies, I'm not going to write the integers from now, I'm going to write it as F1 because I want to emphasize it's multiplicative. So if you take two copies of the infinite cyclic group, you've got to distinguish them because you're not allowed to identify elements. So you've got to call one of the generators A and one of the generators B. And then if you copy this scenario, it means that any element of this free product is going to be some power of A followed by some power of B followed by some power of A. Or if M1 is 0 again, you could start with the B's and so on. And that's completely different from the ordinary product of a cyclic group with itself. The ordinary product, Z cross Z or Z2 or Z plus Z, since it's an abelian group. In the ordinary product, the two generators commute with each other. You know, because if you use the Cartesian product for the integers, and you have sort of, or with even with multiplication, you have sort of you might have A1 and 1b, but these commute. The order, you know, that's defined to be AB, but you can change the order the thing commutes. And that's not what we have here. This is very different. For example, if the two groups were finite, this three product would be an infinite group, whereas the ordinary product of two finite groups would be finite. Okay. Now, in practice, of course, groups are not free. Most of the ones in topology will not be free because there will be relations. So I'm just, if you just come in, I'm just going quickly through this first section because I've got a video online. So the point is, if you understand the definition of a free group, you can understand that any group can be thought of as the image, really, of a homomorphism from a free group. So any group can be thought of as the quotient of a free group by a normal subgroup. Remember, if you have a homomorphism of groups, the kernel is a normal subgroup, and so the image of the homomorphism can always be written as the quotient group, where n is a normal subgroup, invariant by conjugation. So any group can be written in that form, and here are some examples. So really that's the same thing, saying that you've got these generators, and you've got, for a free group there would be no further relations, but in practice for other groups there will be relations. So for example, the simplest non-abelian group consists of you can write it with two generators. For example, you could take it, so S3 is the set of permutations of three numbers. You could write, it's generated by a 2-cycle and a 3-cycle, which you can get everything else from those two elements. But there are relations. In particular, we know a 2-cycle. If we don't know what the 2-cycle is, I'm not allowed to say what A and B are, in a sense. I just secretly know that's what I've chosen A and B to be. But of course, if we don't know what they are, we have to assert that A squared is the identity, B cubed is the identity, and then there's an extra relation that tells you it's a symmetric group, and one way of writing this relation is AB squared is the identity. A slightly more complicated example is the symmetric group on 4 letters, I mean the permutations of 4 objects, and then they've got lots of choices as to how to write the relations. Here's quite a neat way of doing it, in which you choose a 2-cycle, a 3-cycle and a 4-cycle. But this choice is not very helpful for Sn. By the way, this should be S4 like that. For Sn, the symmetries of n letters, you need a sort of a different scheme for it to extend to Sn. So you can try and think, how would I present Sn without talking about permutations? It's going to be generated by a number of letters. By the way, there's one missing here. I've just noticed. This should be C as well. So in general, you'll need more generators and more relations. And then going back to what we've done in topology, if you understand what we did last week, we had a double covering of the sphere to the projective plane. That means the order of the fundamental group of the projective plane, S2 is simply connected, so the order of the fundamental group has to be 2. And there's only one group up to isomorphism of order 2, that's just the group with 2 elements, a cyclic group. So the fundamental group of the projective plane is the cyclic group. So, that's generated by C, and there's a single relation, C squared is the identity. Slightly more complicated is the Klein bottle, and this would be the usual representation using the square, but we know that we can put that in normal form. We can change the arrows and identify adjacent edges rather than opposite edges. So in that case, we get a different presentation, and they're linked by this equation. Incidentally, this equation really also comes from the cutting and pasting operations we talked about some weeks ago, 2 or 3 weeks ago. So the idea is that you can present groups in many different ways, but most groups you need generators and relations, unless they're free. But it's quite a deep subject, because you can be given a set of relations and you don't really know the best way to simplify them. Or you can be given a word in a free group, and you in a group with some relations maybe, and you don't know whether it's equivalent to another word. It's very difficult often to understand how to relate different elements and prove they're the same, because there are different ways of writing the same element once you have relations. So this is explained in this third slide with reference to a very neat example which I'll talk about in the last segment, which I'll have to record. I've still got to record online, in which I wanted to talk about as I promised earlier, I wanted to give at least one example of the fundamental group of the complement of a knot. Okay, so here we take the trefoil knot, right or left, it doesn't matter, and we remove that from R3. So we take R3 minus that loop, that knot, and that gives a topological space, an open subset of R3, which is much more complicated. And its fundamental group is, in fact, for reasons which I'll explain in the last part of this course, the last segment, 10.11.3, the group can be written like that. So it has three generators I've called alpha, beta, and gamma, and three relations, which are all sort of symmetric. It's the cyclic permutation of the first one, because these relations, as I'll explain, come from the crossings of a diagram. The generators correspond to the arcs. I'll explain this online. So remember, the arcs are the things that go from underpass to underpass. So you might have one arc here, alpha, and then a second arc here, beta, and then a third arc, gamma. So you have one generator for each arc, and you have a relation for each crossing. So you've got here three crossings, three arcs. But it turns out that if you do it that way, one of the relations is redundant. So in fact, these are all symmetric. So I can actually remove the third relation. You can prove that it can be deduced from the other two using just group theory. So that's explained here. And then you get that if you rewrite gamma, see from the second relation, gamma is going to be beta alpha beta inverse, which is this here. So that has to equal the other expression for gamma. And if you rearrange this, you get this very neat equation there, that alpha beta alpha is equal to beta alpha beta. So in fact, the group, the so-called knot group for the trefoil knot, could be written as the set generated by, we just need two generators now because gamma is superfluous, and the relation is alpha beta alpha is equal to beta alpha beta. Okay. Now, incidentally, I'll say that afterwards. But you can rearrange that quite easily to show that an equivalent form is that you can change the definition of it. Instead of alpha and beta, I'm using A and B, defined in this way. And then it's easy to see that A cubed is B squared. And that actually relates, as I explained in the video, and I won't do it today, that relates to the way you think of the trefoil knot embedded on a torus, inscribed on a torus, in which the trefoil knot goes 3 times around the outside and twice around the inner tube, so to speak. So that's the 3 and the 2. So you sort of see the geometry from this presentation, as it's called, of the knot group. The other thing I just want to say is that this relation here figures in the video by Thurston. Now, this is an old video which I put online on Keats, and you might think, well, what the devil is he talking about? I'm not 100% sure myself, but I've discussed this with Martin, and we're sure he's talking about the coverings of the complement of the trefoil knot. In fact, he got a Fields Medals for his work on three-dimensional topology, and was a huge influence in the subject. So it's quite interesting that he is really talking about this relation essentially in a sort of popular way. So I recommend that, even though it's not exactly clear what the mathematics going on is, but it's relating to the the 3 manifold you get by removing the tray 4 knot from R3. Okay, any questions? That's just a summary of my first video. Okay, the main thing I want to talk about today is computing fundamental groups using something called the Van Kampen theorem. And I don't have time to prove this, and it's on purpose. I don't want to prove this result. It's part of the proof. It's a bit like the proof of lifting homotopies, lifting paths to a covering space. There's a lot of technical stuff about dividing intervals, getting a loop and rearranging it, and so on. I mean, if you're interested and you're comfortable with topology, I recommend you look at the proof of the versions I'm going to give you. But we're just going to need simple applications of this. We don't really need to know the full, we don't even have to grasp the full statement of it. We just need to be able to apply it to certain fairly simple situations. So just to remind you, we're talking about the fundamental group of a topological space. Strictly speaking, if we want to define that properly, we have to fix a base point. And that gives us an equivalence relations, of course, on loops, because we know that 2 loops starting and ending at the base point are said to be equivalent or homotopic as loops if we can deform one to the other. We have this so-called homotopy, say h, which allows us to actually define a loop for every value of t between 0 and 1. Which is a loop, and it has the property that its endpoints, it starts and finishes at x0 for all values of t. So that's a bit more general than an ordinary homotopy between these maps, which would not insist on where the map starts and finishes, where the loop starts and where the path starts and finishes. So the equivalence classes of such loops give us a fundamental group. And I've explained that if the space is path connected, the base point is not important, in the sense that the 2 different groups you define will be isomorphic, although not in a natural way isomorphic. Now, I want to talk about the Van Kampen theorem, and basically this says, it tells you what to do when your space X is the union of 2 open sets with non-zero with non-empty intersection. So the intersection of 2 open sets is of course open, and we suppose that this is not the empty set. So we are going to relate the fundamental group of the intersection, the fundamental groups of the 2 pieces, to get the fundamental group of X. That's what the Van Kampen theorem does for you. So here's a sort of visualization of the sort of situation you might have. Now, you see, we have these subsets which I've just talked about, the intersection, the two pieces, and the whole space X. If we want to talk about fundamental groups, we need to relate the fundamental groups of these four objects, and we have to do that using the induced homomorphisms. So we need names. I probably won't need them much, but we need names for the inclusion map. So we can put the intersection that's included, that's a subset of U. It's also a subset of V. And then we've got other maps, if we need them, capital I and capital J, that are the inclusion maps of these subsets in the big space. Now, remember, let me just do one example. So here's an example of the situation you might have. So the two-sphere, you want to understand the two-sphere. So the two-sphere, I can't just say, well, I could take the northern hemisphere and the southern hemisphere as closed sets. The intersection is non-empty, but they're not open subsets. So to make this, if I want to split the two-sphere as U union V, I have to sort of I have to slightly enlarge the northern hemisphere. So what I've done here, I've gone down to the Tropic of Capricorn, if you like. I can make the intersection, so U is not just the upper hemisphere, but it goes a bit below the equator, and V is, can't see it because I'm looking from above, but V is the part of the lower hemisphere, but including up to the Tropic of Cancer. So the intersection of U and V is what's called the tropics. It's bound around the equator, and that's an open set. So that would completely fit my hypotheses. The problem with that is that U intersection V in this case would not be simply connected. But anyway, I'll explain how nonetheless you can use this picture. But anyway, let me just say that with this inclusion map, how does that work at the level of fundamental groups? So remember, whenever you have a map between spaces, you get an induced homomorphism between the fundamental groups. So these are all subsets, so I've fixed the base point in the intersection, so we've got a base point. It's the same, this maps to the same base point everywhere. So we've got pi 1 of the intersection. There's an induced homomorphism into pi 1 of U, say. Same base point. And how does that work? Well, you say if I have a loop in the intersection, the equivalence class of that gives me an element of fundamental group here. How do I get a loop in U? Well, a loop means that I'm mapping 0, 1 into this space, but of course I can then compose it with I. I here is just the inclusion, so I'm not really doing anything, but strictly speaking, I have to take gamma composed with I, whatever the map is, and that would be a loop in the second space. So that's how you define this induced homomorphism. We did this before. That's the definition of the induced homomorphism. But beware, because I may be an inclusion, but that doesn't mean that this homomorphism is injective. If you take the example of the sphere, you see if I take a loop around the equator, that's a non-trivial. It's clear that the equator here, I mean, I've said it's a band, but the fundamental group is going to be the same, as I'll explain in a moment, as the equator, which is the fundamental group is Z, or I prefer to call it the free group. And one, in this example, the fundamental group of the intersection is the integers, or the free group on one generator. So it's non-trivial. And I could take gamma to be one turn of this equator, which is non-trivial. It's a non-trivial element. Gamma is not the identity. But when I include it in the upper hemisphere is like a disk. It's simply connected. So I can just shrink the loop up to the, well, in fact, the circle's already here. You can shrink the loop up to the North Pole and it becomes the constant loop. So in this example, that map wouldn't be injective. You see that? And what I'm saying is, just squash everything down, okay? I'm starting really with the band around the equator. There's the equator. I've got a loop that goes, I'm walking around the equator once, let's say flying once around the equator, and that's in S1, the equator is, U intersection V is essentially like the circle. It's what's called homotopic to the circle. I'll explain that in a moment. So you can treat it as the circle, even though it's a sort of second circle. So this loop gamma is not trivial. It's not homotopic to the constant loop. I can't shrink it, because remember we're talking about a surface. I can't shrink it inside the sphere. But once I add the northern hemisphere, I can pull this loop up. I mean, I think there was even an exercise on this. I've got to fix the end point, the base point, but I can pull this loop up. Sorry, so talking about the circles wasn't helpful because that didn't preserve the base point. But I can pull this up and just pull it round until it becomes the constant. Is that clear? So in the northern hemisphere, this becomes trivial. So gamma is not, this is true in U, but not in the intersection. That's what I'm trying to say. Okay, so I'm just saying beware, because even if you've got an inclusion here, the induced homomorphism may not be an inclusion. anyway, here's basically the same slide, except that I've just drawn in all the induced maps. I'm probably not going to use them explicitly, but these inclusions give rise to these induced homomorphisms if we need them. And here I haven't bothered to write the base point, but I'm assuming that the fundamental groups are taken with that base point we've chosen in the intersection. So it's these induced homomorphisms which we can use to relate these four fundamental groups. We've now got four fundamental groups and we need to relate them. And the Van Kampen theorem does that. But before I do that, I need to say something to explain why, when I took what I called the tropics around the equator, that I can treat it as if it's just the equator, as if it's just a circle. Or a similar statement would be if I take an annulus in the plane, that's this region here without the centre, I can treat that, for computing fundamental groups, I can treat that as if it's the same as a circle. Okay? These are homotopic, they're what's called homotopic spaces. And their fundamental groups are equal. And I'll explain that now, because we're going to need that. So that's this next slide. I mean, you know, I hope this is sort of intuitive clear. You know, if we fix a base point, say, let's take the circle here to be the, well, in the picture in a moment it's going to be in a circle, but I've drawn it slightly bigger, so maybe it's the circle to this circle here. Maybe that's what circle I've chosen. But if I have a base point maybe on that circle, but I could take a loop, and a loop in the annulus could squiggle around. There's lots more space for it to fool around, okay? But it's fairly clear, I think, that it will be homotopic to a loop on the circle. I can sort of, it can be deformed, let's say. I haven't defined homotopic. It can be, well, I have of loops. It can be deformed, it can be pushed onto the circle somehow. Okay? I mean, doesn't matter if it backs up on itself. I can just do the same configuration on the circle. It may go back here, but it can do that on the circle. So the class of the fundamental groups will be equal, will be isomorphic. Okay, and that's the idea of this next section. So I'm only going to really talk about a special case here, but here's the general definition, which I've mentioned, I've sort of hinted at before. So first of all, let's talk about maps. So if we have two maps between two topological spaces, so F0 and F1, then they're said to be homotopic if I can deform one to another, just like I did for loops. But I'm no longer, there's no insistence on any sort of what happens for an arbitrary t, because I don't necessarily have base points in this setup. I just have two maps, any two maps. And I say they're homotopic if I can deform one to the other, in the sense that for all t in 0, 1, I can define another map from x to y, so that to begin with, and this is, the whole thing is continuous, it's still in a sense defined on a square, except that we have t defined that way, and here we have the space x, which may not be an interval. So we have, this is the domain of h, but when t is 0, we have the original map f0, and when t is 1, we have the map f1. That's the idea of a homotopy. So it's just like homotopy of loops, except there's no condition about what's happening here or here. And then using that notion, you can say what it means for two spaces to be homotopic. So now these were maps. Now we're talking about two topological spaces. They're homotopic if we can find a pair of maps, one going from x to y and the other going backwards, not necessarily the inverse, because f may not be bijective, that's the point. But we want that when we do f and then we do g, it's probably impossible that that be the identity, but I can insist that it's homotopic to the identity on x. And I can insist that if I do g first and then f, it may not equal the identity, but it's going to be, I'm going to insist that it be homotopic to the identity on y. And that's the notion of two spaces being homotopic. I only want to talk about a special case of that, in which the special case is in which H is a subset of Y, in which case I can insist that when I do F and then I do G, I could insist this is actually equal to the identity on X. That makes sense. I could insist on that. Whereas this relation stays the same. And that's the setup in which you have what's called a deformation retract. So the special case I'm mainly interested in is that in which X is a subset of Y. The map F is the inclusion map. And so we insist that F followed by G, or I followed by G in this case, is the identity on X. And this is explained in this example here, in which I put my circle in on the inner boundary rather than in the middle, but it's what I was trying to say before. So in this case, Y is the yellow region, the annulus. X is the circle. Doesn't have to be the boundary, it could be in the middle, doesn't matter. But there's an obvious map that I can use to send, the map G has to go from Y to X. And it has to essentially be the identity on X. That's what this equation is saying. It's really saying that G of X is equal to X for all X in X. That's what this equation is saying. And you see, the obvious thing I can do is take, this is radially symmetric, so I can just take any element in Y and just map it down to the circle radially. Okay, so that's my map G. It just moves everything to the circle. And that will satisfy this condition. That if I do G, because this is a deformation process, I can do G completely, or I can sort of, for t is equal to a half, I can move half the distance to the circle. Okay? So I can either start, when t is 0, I do the identity on the yellow region. When t is a half, this point near the boundary moves halfway to the circle. If t is 3/4, it moves 3/4 the way, and so on. So at the end, when t is equal to 1, I've moved everything from the yellow region onto the circle. So that's a deformation, really, of G to the identity map on the to the map. Well, it's a deformation that takes the identity at the beginning, that does nothing on the yellow region, to the extreme map that pushes everything to the circle. So that means that X is what's called a deformation retract of Y, typo here. It's actually, strictly speaking, it's a strong deformation retract because of an extra condition I put here, but let's not worry about it. And that makes it easy to actually prove when you have a deformation retract. If X is a subset of Y and it's a deformation retract of Y, then it's very easy to prove that the fundamental groups are isomorphic. That's also true whenever X is homotopic to Y, but you have to fiddle around with base points which move around. So, but in this special case, it's quite easy to see. And so in particular, the fundamental group of this yellow annulus is the same as the fundamental group of the circle, because you can relate loops by homotopies. So I just needed that because in my examples we won't necessarily have honest circles. We'll have things that are close to circles, and we want to assert that their fundamental group is equal to that of the circle. Okay. So here's the first version of Van Kampen's theorem in a very, very special case in which the intersection is simply connected. So we have this set up. Remember that X is the union of two open sets and their intersection is non-empty. And these have to be open subsets. And in that case, the fundamental group of X, if we assume that the intersection is simply connected, that was not the case for my spherical example in which the equator was not or the tropical region was not simply connected. But if it were, then it would be if I went up one dimension incidentally. I could write the three-sphere as the union of the sort of northern hemisphere and the southern hemisphere, and in that case the equator would be homotopic to S2, which is simply connected. So that argument will work for the three-sphere, for higher dimensional spheres, but not for S2. But anyway, we're now assuming that the intersection is simply connected. In that case, the fundamental group is just the free product of the two fundamental groups of the two pieces, with no interaction between them, no relation between them. So that's so here's an example of that. Suppose you want to work out the fundamental group of a figure 8, not the figure 8 knot, but a figure 8. So there's a topological space. It's a curve in the plane. It's just a figure 8. It's the same really as two circles stuck together, which is exactly what we get when we look at the boundary identifications to get a torus from a square. Because to get a torus from a square, remember, we had the square with the two circles. Well, this edge A is really the same circle, and we've got another edge, another circle here, which is B. And the code is AB, A inverse, B inverse, but A and B are really both circles, and they're joined together because this 4 vertices on the square becomes a unique vertex in the quotient. But I'm excluding the inside. I'm not including the inside here. I'm just looking at the boundary of the square. You get these two circles. Now, I want to compute the fundamental group of these two circles. It's called a wedge of two circles. It's written S1 wedge S1. S1 is a circle, or topologically a circle, homeomorphic to a circle. Well, you know, I can't take the two circles because they're not closed subsets, but I can extend them a little bit, just as I did for the northern hemisphere. So we could take the blue circle on the left and we could make it a bit bigger, like that. We could just extend it beyond the vertex, say to here. That's then an open subset. But it's clear that this figure here, which is just this set here, this is this is homotopic. I mean, the circle, that's this thing here, should have written it the other way around, is a deformation retract of that. Because I can define a map G, just as I did for the annulus. G could sort of send the elements in these antennae and sort of shove them down to the vertex. And clearly there's no other, we can't get any other loops, non-trivial sort of loops, by adding these two little pieces there. We would if we closed them up, but they're not closed up. So the fundamental group of this U will be that of a circle, which is just the free group. It's just the integers, if you like, or it's the free group on one generator. But we have to use different symbols, so we could think of sort of one of the generators as coming from this loop A, which goes around this circle here, and the other one is coming from B, which goes around this circle then. There's no relation between A and B. So an arbitrary loop in this space here would be just a long word in which you might do 3 times round A, then minus once round B, then 4 times round A, then 50 times round B, and so on. And you can't move those letters around. Okay, so that's the fundamental group. Of course, the intersection is, of course, the cross, which is simply connected. So I meant the cross, not X. The intersection, I'm taking obviously the red circle, I'm extending that the other side a bit as well. Let's become green. So the intersection of these two open sets is this cross. And that is simply connected. Because again, that's I can do a deformation retract and send everything down to a point in the vertex. So pi 1 is trivial. So we satisfied that hypothesis. So that's the first. That's the first case, the sort of easy case of Van Kampen's theorem. Notice that I'm saying this is isomorphic to that, but the isomorphism is going to come about by means of these induced maps, which I mentioned earlier. So in order to think of, this is a free group, but it's going to contain pi1 of u as a subgroup. And to think of pi1 of u as a subgroup of X, we've got to use these maps here, in particular this one here. So it's really a consequence of this theorem that the induced maps, these two induced maps here, are going to be injective in this case. These will be injective if the intersection is simply connected. That's a consequence really of Van Kampen's theorem, version 1, because the fundamental group of X is the free product of this with this. So there's no sort of relation. So that forces these maps to be injected. Okay, now what about the second version? Oh no, I've got something more to say here. So why am I interested in this example? Because it comes from the torus. And I don't really want to compute, I'm not interested in the fundamental group of this figure. I'm only interested in it because it's the boundary, it's the part of the torus. I mean, when you do the torus as a quotient, you put it in R3, you can think of this wedge of circles as like your bicycle tube, with the circle going around the inner tube and the circle going all the way around. And that's what you get from the boundary of the square. But then we have to fill that in and ask what is the fundamental group of the torus. This is a subset of the torus. These two circles wedged together at this point is a subset of the torus. But we want the fundamental group of the torus. Now we know what that is secretly. Well, actually, I've given another example here. I don't know why I've changed the examples. We've spoken too much about the torus, but here's an example of genus 2. So in this case, we could start with an octagon, and we have that relation around the outside. So this is just motivational, so let's skip that, so I'm going to come back to that. But that's why I'm interested in these graphs here, because they come from the boundaries. When you represent the surface with a polygon, remember, when you take the normal form of the surface, all the vertices are the same. So when each pair of edges will give you a circle. And so in the case of this normal form, we'll actually have 4 circles stuck together. That will be the boundary. That will be the quotient. That will be in the quotients in the surface of genus 2, which secretly we know looks like a torus with sort of 2 holes. We will see this configuration because that comes from the boundary of the octagon. So we need to know. We now know that the fundamental group of this rows, 4-leaved rows, as it's called, is just a free product with 4 factors. Now, to come on to the second version then, and I think I best explain this by means of an example. So remember, most groups are not free. We're very lucky in this situation in which the intersection is simply connected. Remember, simply connected means the fundamental group is trivial. So if the fundamental group of the intersection is trivial, we know that the fundamental group of this big space X is just this free product. No relations between these two groups. But in general, groups, most groups are not free, and we could expect in general that the fundamental group will be obtained from this, but with some relations. And that's really the statement of the main so-called Van Kampen theorem, or sometimes called Seifert-Van Kampen theorem, states that the fundamental group of X, of our union, is not in general free, but it's the quotient of the free group by some normal subgroup, and this normal subgroup is generated by these elements which arise from the intersection. Now it's easy for me to state that, Well, what am I trying to say here? You see, we've got the fundamental group of the intersection. We've got the fundamental groups of the two pieces. And we've got the fundamental group of X, and there are these homomorphisms between them. Now, think of the case in which, just for sort of thought processes, suppose all the spaces are equal to X. That's allowed, right? Because X is an open set of itself. X is an open subset of itself. So you could take these all to equal X. Now, in that case, you know, obviously the fundamental group of X is not the free product of itself with itself, because that would be too big, because in the free product there's no relation between the two factors. So I've got to sort of get rid of, you know, I could start with the fundamental group of X, free product, the fundamental group of X in this case, but I've got to get rid of something. I've got to take some sort of quotient. And what's going on is that you've got elements in here which really are mapping, although they're mapping to different things in here, because this is a free group and there's no relation between the factors. In practice, all the stuff coming from here is the same, whether it ends up there or there. It's got to be treated as the same. So we've got to identify stuff in here. Anything in here that comes from here has got to be identified with the corresponding image in here. And that's what this is doing. It's just saying that if we have something, if we have a class H in here, then of course I star of H would be here, J star of H would be here. But by the time they map into the fundamental group of X, we've got to think of them as the same. In other words, the inverse of one times the other has got to be thought of as the identity. So that's the set of elements we want to render as the identity. And the way to do that is to take the smallest normal subgroup that contains them and quotient out by that group. So that's the idea of Van Kampen's theorem. And it involves this slightly sophisticated notion of what's called an amalgamated product, in which you sort of have a square of homomorphisms. Really, this would normally be written as a square of homomorphisms, and you've got something that feeds into both of these, and the images have to be identified in the final product. Okay, I don't want to say more about that. Let's go to examples. So let's now apply this to this octagon, this genus 2 example. So remember, just forget the insides for the moment. Here's the red octagon. The red octagon is the model, or can be the model, for an orientable surface of genus 2. We can get an orientable surface of genus 2 by taking the normal form around the boundary, which is this word here, which means we identify the edges around the boundary. We have A1, B1, I'm not going to label them, A1 inverse, B1 inverse, well, I'll label one of them, A1, B1 inverse, then we have A2, label that as well, B2, A2 inverse, B2 inverse. That's the way. If we do those identifications, then all the 8 vertices will be the same in the quotient, because from the edges we get that all the vertices are the same. So all these edges really represent circles. Well, there are 4 distinct edges because they're identified in pairs, so we get 4 circles. So as I explained before, the vertices are all the same, so we get these 4. If we just take the boundary in the quotient, we get these 4 circles stuck together. So if we try and apply now I want to try and apply, this is the crucial thing, I want to try and apply Van Kampen's theorem. And I need to split, remember the surface is the quotient of this octagon with the inside included. Now, I could remove a point from the octagon, just remove, say, the inner blue octagon, the tiny blue octagon on the inside. If I do that, then I get an annulus. And from what I said before, the fundamental group of that annulus will be the same as the fundamental group of the boundary, because the boundary is a deformation retract of the annulus. And we know what the fundamental group of that is. It's going to be the free product of the four, with four factors, one corresponding to A1, B1, A2, B2. So we know what the fundamental group is of this annulus if we remove something in the middle. But to get the whole space, we've got to include a disk in the middle that covers what I've removed. So what I've done in this, to apply Van Kampen's theorem, is I've taken U to be the annulus. You see, purple is meant to be blue plus red. So you've got the red annulus that includes the purple annulus, and we've got the blue annulus, so the blue disk, which includes the purple as well. Okay, so V is the blue disk that includes the origin and goes up to here. The intersection of U and V is the purple annulus. Okay, so U is homotopic to the boundary, which when you look at it in the quotient is just the wedge of four circles. That's this configuration. V is just a disk. I'm including the origin. It's just a blue disk. So that can be shrunk. That's the point is a deformation retract of the disk. So the V is essentially like a point. The intersection is this purple annulus, which is essentially a circle, because I can take a circle in the middle and everything else, writing it down explicitly will be more difficult, but I can think of the purple annulus, the circle as a deformation retract of the purple annulus. So we know what all the fundamental groups of these things are. Okay, so the fundamental group of Rm, which is now the union of U and V, is the fundamental group of U. Well, we know what that is. It's the free product on four generators. There's a typo here because there are four circles. The fundamental group of V is trivial, so we don't even have to care about H. Excuse me. So we actually just get, well, we do care about H actually a bit, because we have to worry about the relation coming from the intersection. So we've got the free group on four generators, but we have to worry about the relation coming from the intersection, sorry, the relation coming from the intersection, which is this, essentially this circle. So if we take a loop at just one turn of the circle, that generates the fundamental group of the circle. Then we insert that loop into U, which effectively now we're just thinking of as the boundary. So the image of that circle as a loop will just be going round, will just be the circle going once around the boundary. So according to the theorem, that image has to be treated as if it's the identity. So the theorem is telling you that this circle maps to this loop here, and that has to be treated as if it's the identity. And that's what the fundamental group of the surface is. So it's completely free on four. It began, to get it, we start with a free group on four generators. So that would be this without any relation. But then because we have to take this H business, that corresponds to the fundamental group of the intersection, we have to sort of relate the fundamental group of the intersection. So I've taken a loop around the intersection and relate that to the fundamental group of U, and anything we get has to be thought of as the identity. That's essentially here, because J star is trivial, V is trivial, so we can get rid of J star here. So we've got to make sure that these elements here, I can forget the inverse as well, are treated as the identity. And all I'm saying is that if I take a loop, actually I called it alpha 1 normally, the loop that generates the circle. If I take I star of this, that will be this word, because I'm just saying when I push the circle out to the boundary, I get just the boundary code, as I called it, going around the boundary. Okay, so that's the proof. If you believe Van Kampen's theorem, which admittedly we haven't proved, that's the proof that the fundamental group of this surface, and you can imagine all the other surfaces, at least without boundary. It's a little bit more complicated with boundary. but at least the surfaces without boundary, all you say is that it's just generated by these letters we used in the normal form. You have to use the normal form because we want to make sure that each edge is a circle, so that defines a loop. So all the vertices must be the same, and that only generally happens when it's in normal form. But if you take the normal form of the surface, that is exactly the unique relation you need to define the fundamental group. Okay, I'm going to finish there. There's an extra slide, which I won't display, but it just lists the different types of surfaces and the relations you get. Well, I'll just show it to you, but I'm not going to say anything. So just if you take the non-orientable one, remember the normal form was C1, C1, C2, C2, and so on. But when you think of that as an element of the fundamental group, you can just replace C1, C1 by C1 squared. So we now know, using Van Kampen's theorem, the fundamental group of all these surfaces. Okay, I'll stop there. Thanks for turning up. Thanks for following me to the end. Use Keats to look up material after the break. I'll try and see material. You'll be asking me about the exams and so on, but I won't respond to anything about that until the new year. Okay, in which I'll put material on Keats to help you understand what you need to know. Okay, thank you. I'll be in Bush House if you need me.